Chapter 9, Rotational Motion. This lecture will help you understand angular displacement. If a body moves so that every particle of the body follows a straight line path, then the motion of the body is said to be rectilinear. Any two particles of the body travel the same distance in the same time along two parallel straight lines. In the figure, x of t represents the position of the particles along the direction of motion as a function of time t. Given the position of the particles, x of t, we can calculate the displacement, velocity, and acceleration. Curvilinear motion is defined as motion that occurs when a particle travels along the curved path. The curved path can be in two dimensions, such as in a plane, or in three dimensions. This type of motion is more complex than rectilinear motion. The figure shows the curvilinear path of an orbiting satellite. Rotational motion is the motion of objects that spin about an axis, like the blade assembly of the wind turbine. The Earth spins about its axis and exhibits rotational motion. Rotational motion is the motion of a wheel spinning on its axle, a drive or crankshaft, or an electric motor. A revolution is one complete rotation of a body through 360 degrees. We use the angle theta from the positive x-axis to describe the particle's location and call that angle the angular position of the particle. The angular position is positive when measured counterclockwise from the positive x-axis. An angle measured clockwise from the positive x-axis has a negative value. We have been using degrees as our standard unit of measure for angular position. However, when we discuss rotational motion, we use the radian as the standard unit of angular measure. There are 2 pi radians in a complete circle. With that information, we find that 1 radian is just under 57.3 degrees. A complete revolution is 360 degrees, or 2 pi radians. The arc length of the circle is the part of the circumference of the circle between 2 radii separated by a central angle. If we have an angle of 2 pi radians, 360 degrees, we have traveled through an arc length, which we call S, of 2 pi times r, which is the circumference of the circle. If we have an angle of pi radians, 180 degrees, we have traveled through an arc length of pi times r, which is half the circumference of the circle. If we have an angle of pi over 2 radians, 90 degrees, we have traveled through an arc length of 1/2 pi times the radius of the circle, which is 1/4 the circumference of the circle. If we have an angle of pi divided by 4 radians, 45 degrees, we have traveled through an arc length of 1/4 pi times r, which is 1/8 the circumference of the circle. The arc length S is the central angle, theta, in radians multiplied by the radius of the circle, r. The arc length is the distance that the particle has traveled along its circular path. 1 radian is the angle at which the arc length S has the same length as the radius, r. As an example, let's convert 10 pi radians to A, revolutions, and B, degrees. Since 1 revolution is equal to 2 pi radians, our conversion factor is 1 revolution divided by 2 pi radians. Multiplying this out yields 5 revolutions. The object has made 5 revolutions if it has traveled 10 pi radians. Since 360 degrees is equal to 2 pi radians, our conversion factor is 360 degrees divided by 2 pi radians, yielding 1800 degrees. 1800 degrees is equivalent to tracing out 5 complete circuits of a circle. We define the linear displacement as the change in position independent of distance traveled. If we start at position x sub I and end at position x sub f, then the displacement is x sub f minus x sub I. Angular displacement is the angle through which a rotating body moves. It is the change angle. We start at angle theta sub I and end at angle theta sub f. The angular displacement is theta sub f minus theta sub I. The angular velocity, or the angular speed, is defined as the rate of change of the angular displacement. It is the angular displacement divided by the time interval. It is given the symbol, the Greek letter omega. A motorcycle wheel turns 3,600 times in 6.40 minutes. What is the angular speed in revolutions per minute? The angular displacement is 3,600 revolutions. The time period is 6.40 minutes. The angular speed is 3,600 revolutions divided by 6.40 minutes, giving 560 revolutions per minute, or 563 RPM. The time interval it takes an object to go around a circle once is called the period of the motion. We give it the symbol of uppercase T. In one time period T, the object travels around the circumference of the circle. We can also specify circular motion by its frequency, the number of revolutions per second. If an object has a period of 1 second, it rotates at a frequency of 1 revolution per second. If an object has a period of half a second, it makes 2 complete rotations in 1 second and has a frequency of 2 revolutions per second. If an object has a period of 1/10 of a second, it has a frequency of 10 revolutions per second. We can define the frequency as 1 divided by the period. The SI unit of frequency is the inverse second, which is also known as a hertz. Angular speed is the absolute value of the angular velocity. Angular velocity has a direction. The wheel on the left is turning counterclockwise. We call that a positive angular velocity. The wheel on the right is rotating clockwise. That is a negative angular velocity. They have the same angular speeds, but opposite angular velocities. The angular speed is related to the period t. If an object rotates 1 complete revolution, it has gone through an angular displacement of 2 pi radians. The time of 1 complete rotation is the period t. So the angular speed is 2 pi radians divided by the period. Since the frequency is 1 over the period, we can write the angular frequency as 2 pi radians times the frequency f. As we see in the diagram, the point at the top of the circle is moving to the left. We can define the velocity of the point of that time. We can find the linear speed of a rotating object. We call this the tangential velocity. It is the velocity at the tangent to the circle and is at right angle to the radius of the circle. In a previous chapter, we defined the linear velocity as the displacement divided by the time. In circular motion, the distance traveled is the arc length, but the arc length is the central angle times the radius. In terms of angular displacement, the arc length s is the radius times the change in the angle delta theta. The linear speed is r times delta theta divided by the time interval. Rearranging just a little, we find that the linear speed is r times the rate of change of the angle. But the arc length is also the distance traveled, what we call delta x in linear speed, which means the distance traveled is r times delta theta. The tangential speed is the radius times the angular speed. A wheel of 1 meter radius turns at 1000 RPM. Express the angular speed in radians per second and find the linear speed of a point on the rim of the wheel. The angular speed is given as 1000 RPM or 1000 revolutions per minute. There are 2 pi radians per revolution, so we multiply by 2 pi radians divided by 1 revolution. Since we are given a speed in revolutions per minute, we must convert minutes to seconds and must multiply by 1 minute divided by 60 seconds and get an angular speed of 105 radians per second. The linear speed is the angular speed times the radius, or 105 radians per second, times a radius of 1 meter, giving 105 meters per second. Notice we do not use the units of radians in our final answer for velocity. They are just dropped. Earlier, we found the linear displacement during a time interval is the linear velocity times the time interval. Similarly, the angular displacement for uniform circular motion is the angular velocity times the time interval. We say velocity here because we must take into account direction of rotation.